I'm going to show now how to perform cross-section optimization in AXISVM with the brand new component group of the GrasshoppertoAXISVM add-on. The components can handle steel as well as timber design members. In this example, I work with a parametric steel frame structure, but the usage of components would be exactly the same for timber design members as well. You can see that I have steel design members on the vertical and horizontal beams, and the structure contains some members with unacceptably high utilization values. Our new components can be found under the Optimization subcategory of the AXISVM tab. There are 5 components in total, and I'm going to introduce them one by one and show how they must be connected with each other. I focus first on the general optimization settings. This component covers the encircled part of the cross-section optimization form. These settings are common for parametric optimization and for optimization from predefined shapes. User may select the objective of optimization using the value list, set the maximum allowed utilization, and set the Boolean inputs of the optimization checks to tell which of them need to be considered and which not. All these inputs are set to true. This means they are going to be considered by default. The strength checkbox is not represented on the Grasshopper component. It is always considered as true input in the background because it is essential for the optimization. Thus, it is permanently selected even in AXISVM. I go on to the settings of a parametric optimization group that is going to contain the vertical design members. The top 3 inputs are the name of the optimization group, the design members to be added to the group, and the general optimization settings that I have just introduced. The cross-section parameter on the left side contains the cross-section of the design members, and with the new deconstruct cross-section component, its cross-section parameters are available and can be used to set up the cross-section parameter limits of the parametric optimization group easily. These values are always in meters in Grasshopper. To define the parameter limits, the most simple way is to connect a numeric value, for example, taking the appropriate output of the deconstruct cross-section component. I do this for the height and width. With this approach, the parameter limits are calculated according to the default rules of AXISVM. For the 0.27 meter height, the lower limit is the half of this value, and the upper limit is equal to 2 times this value. The delta step size is set to 0.05 meter in this case. Same logic is applied for the width. If I would like to fix any of the cross-section parameters during the cross-section optimization, the easiest way is to connect a true value as input that sets the given parameter to fix immediately. And I show a third option. I would use this if I would need completely custom limits. In this case, I would take the AXISVM optimization parameter limits component and set each value as I wish. It is sufficient to fill those inputs that are relevant for the current cross-section shape. The 3 bottommost input parameters tell AXISVM whether I would like to set a custom limit for the iterations and how many % of the most utilized beams should be considered during optimization. The input parameter called beams % accepts round values that may be divided by 10. To ensure this, I took a number slider going from 1 to 10, and I set an expression x multiplied by 10 to provide valid input all the time. To really understand the meaning of these inputs, I displayed a screenshot of the AXISVM user interface again, and I mentioned that the cross-section optimization in AXISVM may happen 2 ways currently. In this case, In case of PSO optimization, the form looks like this, and you can see easily how to set custom iteration count and how to change the considered beam amount. However, in case of simple optimization, these settings are simply not relevant, not even available. AXISVM decides which optimization method is going to be used for the groups. So it works to define these input parameters in Grasshopper, knowing that they are used only if PSO optimization is performed. Let me fix the flange thickness parameter as well to speed up the upcoming optimization process, and then go ahead to the configuration of optimization groups for optimization based on predefined shapes. I'm going to set up a group for the horizontal steel design members. The first three inputs of the component are the same as we saw earlier at the parametric group: name, design members, and the general settings. The cross-section of the design members is IPE 400. I select some cross-section candidates from the same cross-section table. This is very quick since the AXISVM cross-section component is improved and allows multiple selection now. I may take cross-sections that are already part of the model as well. I connect the list to the optimization settings component. The component still needs lower and upper limits for cross-section height and width. I use the deconstruct cross-section component, and first I connect the height value to hmin and hmax, and the width to bmin and bmax, then set expressions to each parameter. The lower limits are calculated as half of the h or b value. The upper limits are equal to 2 times the h or b value. I could also do that I connect my cross-section candidates into the deconstruct cross-section component, search for extreme values of the height and width, and connect those extremes to the input parameters. If this is done, I can check the limits, for example, in the text description of the optimization settings. We arrived now to the AXISVM cross-section optimization component, where every setting I explained can be combined together and the optimization process can be started. This component is able to run optimization for either steel or timber design members. So it works for both, but they can't be combined within one optimization. The first input is AXUP, because this component communicates with AXISVM. The second input gathers the list of the optimization group settings, both parametric group settings and settings with predefined shapes can be connected, as many as you want. The only restriction is that one specific design member can be part of one single optimization group only. If it appears in more group settings, it is removed from the earlier groups. Error message is, of course, displayed about this information, and the design member is considered in its last group only. In my list, I have the two settings introduced earlier. The first one is the parametric group setting, and the second is the group with predefined shapes. I chose an envelope and critical case for this demonstration, and I show you in AXISVM that the envelope result case results in higher utilization. Before I start the optimization with the Boolean input, I move the toggle below the panels because I would like to show also the information that appeared during the optimization process. If I start, the parametric group is immediately created. Then the candidates of the other group are added. And when the groups are created, the optimization starts for the first result case and first group, which are the envelope case and the parametric group in this case, the progress is displayed continuously, and in the end, the finished or finished with errors message appears. In the second case, you would see some error messages in the second panel, of course. If every result case and group are checked, the done output is set to true, so the process is completed. To have the optimization results, there is no need to use any extra component. The X results output contains the available data for each result case and optimization group. The first index of the branch path stands for the result case. In this example, 0 is for the envelope and 1 is for the critical case. The second index belongs always to the optimization groups. In this case, 0 is for the parametric group, 1 is for the group with predefined shapes. Before going into more details about the results, I still show that the optimal cross-section output contains the cross-section parameters for the group with predefined shapes. If I display the contents, you can see that the optimization of the envelope result case shows necessity for a bigger cross-section to compensate the higher utilizations as expected. Then I change the view to talk more about the results, and I focus on an Explode3 component that is connected to the X results output and provides the 4 branches on separate outputs. The parametric optimization results of the vertical design members are collected in the panel on the left, and the optimization results for the horizontal design members based on predefined shapes are collected in the panel on the right. Beside the sketches, the data of the original member cross-sections are displayed. The optimization result descriptions always contain the group name, the optimization type, and the result case in the header. Then the utilization and cross-section data. I take the new AXISVM deconstruct results component to access the results directly and connect the branch 00 and 01 to one and the other component. You can see that the output parameter list is automatically adjusted, and at the bottom of the components we see that cross-section optimization results are deconstructed. The suffix par is for parametric groups, and the suffix ps is for groups with predefined shapes. The unnecessary output parameter at the bottom may be removed by right-click on the component and using the Match Outputs feature from the pop-up menu. The header output contains the names of the other input parameters, thus it may be used as a table header. Then the result case information, the optimization group, and its type is available. The details of the optimal cross-section, then the utilization values, and the change in the mass is available. The output parameter names are the same for the group with predefined shapes as well, but here we may get not only one value for one input, but a list of results, similar to AXISVM. If I open the cross-section optimization in AXISVM, you can see that the groups and their settings are stored, but the results not. I start the optimization process, first for the critical min-max. This is slightly speeded up in the video. You can see that these results match the values that I have in the bottom of the big panels. The only difference is that AXISVM assigns a cross-section name to the outcome of the parametric optimization. In Grasshopper, the cross-section name is created considering the cross-section parameter values. Then I run the optimization for the same envelope case I used in Grasshopper. And if I click on the arrow beside the cross section, then I see the same two cross sections for the group with the predefined shapes as I saw in Grasshopper. Thank you for watching.